So now we will learn the method of partial fractions for integrating proper rational functions. I'm going to skip all the algebra. I'll tell you what we're doing, but then hopefully you learned the algebra from the last video and we won't have to confuse so many issues. We'll just concentrate on integration. So our first example, we first check and make sure it's proper, and it is degree 1 over degree 2. And we check to see if the denominator is factored. This is a difference of 2 squares, so it is not factored, and the first thing we do is factor the denominator. So we have x plus 3 over 1 minus x times 1 plus x dx. So now we will take this and set it up using partial fractions. And so I would say, and I'm going to solve for these fast, I would say, well, x plus 3 over 1 minus x times 1 plus x will be equal to a over 1 minus x plus a constant b over 1 plus x. That's what the partial fraction decomposition will look like. If you clear the fractions and let x be 1 and let x be minus 1, you quickly will find a and b. So I'll just put this implies via the algebra that we learned in the last video that a is equal to 2 and b is equal to 1. So this problem reduces to the integral of 2 over 1 minus x, which I'll take the 2 out and write 1 over 1 minus x dx. That's 2 over 1 minus x plus the integral of 1 over 1 plus x dx. And we see these are natural logs. Now don't forget, it's easy to forget at this point, if this is 1 over u du, then the du is minus dx, so I need to supply a constant factor of minus 1 and minus on the outside. Now here, if u is 1 plus x, du is dx, so there's no adjustment necessary. So integrating, we have minus 2 times the natural log of the absolute value of 1 minus x plus the natural log of the absolute value of 1 plus x, and we're done. Our second example is the integral of a rational function that is not proper. First you check the degree of the top is greater than the degree of the denominator polynomial, so we have to divide the denominator into the numerator, and I'm going to skip the algebra, and you should pause and make sure that you get the same thing. So we get a quotient of x minus 2 plus the remainder 5 over the denominator polynomial x squared plus 2x plus 2. So of course integrating x minus 2 will just be 1/2 x squared minus 2x. So our problem here, let's write that as, I won't integrate it yet, x minus 2 dx, and then we're going to have plus, well, I could leave the 5 there, let's leave the 5 there, 5 over x squared plus 2x plus 2. Now this is proper, so we wonder, can we factor it? Well, let's check the discriminant. b is 2, c is 2, a is 1. So b squared minus 4ac for this polynomial would be 2 squared is 4 minus 4ac. 4 times 1 times 2, we see it is less than 0. Therefore, this is irreducible. So we have no partial fraction that is going to split into. The denominator is already irreducible. We can't factor it. So what you do when you get an irreducible quadratic in the denominator, like this, you will complete the square. So Well, I'm going to circle this in green, and let's not forget about it. But right now, we're going to concentrate on this integral here. So let's see, I'll switch colors and do that in yellow. I want to complete the square, so I'll have the integral of 5 over. Now, I want to take half the coefficient of x, which is 1, and square it, so that I get x plus 1, the quantity squared. And then I have x squared plus 2x plus 1, so I have 1 there. Or you could add and subtract 1, and you would have this. So, well, let's change it to u. If u is equal to x plus 1, du is dx. So this changes to the integral of 5. I think I'll pull the 5 out. It's obvious that's what we should do. 1 over u squared plus 1 du. And that's arctangent. So this is 5 arctan u, which is x plus 1. So now let's write our answer. I'll do that back in white. We have the integral of x minus 2 up here that's circled. And that will give us 1/2 x squared minus 2x. And then we have this, the yellow, plus 5 arctan of x plus 1 plus a constant. So we had an improper rational function. We divided out the denominator and came up with a simple little polynomial plus a rational function with an irreducible quadratic denominator, which cannot be factored, and therefore we have no partial fractions to set up. And we just go ahead and integrate. Now, if I give you an irreducible factor or an irreducible denominator, when you set up your partial fractions, or in this case there was none to set up, just complete the square on x, and it will be probably an arctan or an arctan plus a log. So I'll do an example like that also. Okay, here's another rational function, degree 0 over degree 3. It's proper. The denominator is factored. X squared plus 9 cannot be further factored, so x squared plus 9 is an irreducible quadratic, and x plus 3 is linear. We know that this will set up a partial fraction decomposition that will look like, well, I'll put a over x plus 3 plus bx plus c over x squared plus 9 dx. So we have to set these two equal and clear the fractions and solve for a and b just as we've done before. And I won't show you all those details in this video. You should definitely pause the video now and see if you can solve for a, b, and c. And you should get this. The integral of a is 1 over x plus 3 dx, I'll split the two, plus the integral of b was -1 and c was 3. So it's minus x plus 3 over x squared plus 9 dx. So this, well, if u is x plus 3, du is dx, this is 1 over u du. So this is very fast, natural log of the absolute value of x plus 3. So let's not forget it. We'll have to come back and remember to put this in our final answer, but we need to integrate this over here. Now I can see that if I didn't have the plus 3 there, I could turn this into a natural log of the denominator. And if I had a 1 instead of the 9, I could turn the other half of the sum into an arctan. So let's split this into two integrals, and I'll write, well, I think I'll write minus the integral of x over x squared plus 9 dx, and then plus 3 times the integral of 1 over x squared plus 9 dx. The first of these two, this one, is simple because we see if u were x squared plus 9, then du is just 2x dx. So I need a 1/2 there, and we had the minus. So this one is another easy one. Minus 1/2 the natural log of x squared plus 9. So we've got to remember this one to come back and get when we're done. But now we have this over here, which does look different, and let's see, I'll do it in yellow. No, maybe I should pick red. Let's do this one in red. Alright, the problem is we wish it was x squared plus 1, and then we would have an arctangent, or maybe u squared plus 1, and we can make it into that. Look at the quantity x squared plus 9. We can write that as factor out the 9, and then we have to divide each one here by 9 plus 1, right? I can write that expression this way, and x squared over 9, well, that's equal to 9 times x over 3, the quantity squared, plus 1. So this is just a little trick that you can do sometimes to make life easier. So let's see. Let me move down a bit, and I'll change colors and go back to yellow, and let's finish this problem. So I'm going to write this one here as, well, I have my 3, and I'm going to have 1 over, and I'm going to pull out the 9 out here. Remember, it's in the denominator. The factor of 9 is in the denominator, so I'm pulling out 1/9. And then I have left x over 3, the quantity squared, plus 1 dx. Well, if u is equal to x over 3, then du is 1/3 dx, and I need to adjust with a factor of 3 on the outside. And we have arctan u. So this is 9 over 9, which is 1, and it is simply arctan of x over 3. So now we want to put together our final answer. We had the natural log of the absolute value of x plus 3 minus 1/2 the natural log of x squared plus 9, and then this little tricky one, we have plus arctan of x over 3 and add a constant. So this is the answer, and if you really want some good practice, why don't you differentiate it with respect to x and see if you get back to the original rational function. In this problem, we see that the rational function is proper, degree 1 on the top, degree 2 on the bottom, and the polynomial, the denominator polynomial, b squared minus 4ac, in fact, is 0. So we should be able to factor this, and in fact you see it's x plus 2 squared. So we factor the denominator, 3x minus 1 over x plus 2, the quantity squared, dx. This will give rise to, as we saw in the first part 1, this will give a partial fraction decomposition of a over x plus 2 plus b over x plus 2, the quantity squared, dx. So I need to solve for a and b, and I'd like you to put this on pause and you solve for a and b and see if you get the same thing that I do. So you set up your partial fractions on scratch paper and you cleared your fractions and solved for a and b, and I got a is equal to 3, a equals 3, and I got b is equal to negative 7. So I will split these apart and write it as 3 times the integral of 1 over x plus 2 dx plus, or I should have put minus, I guess. Here, let me erase that. Minus 7 times the integral of 1 over x plus 2, the quantity squared, dx. If u is equal to x plus 2, then du is dx. So this one is 3 times the natural log. Now over here, well, let's go ahead and write that. 3 times the natural log of the absolute value of x plus 2. Okay, now let's check this one. This would be, u again, would be x plus 2. This integral, and du is dx, this integral is the integral of u to the minus 2 du, which we know is minus u to the minus 1, or minus 1 over u. So this one will be plus 7 over u, which is x plus 2, and add a constant. So if I have gone a little bit too fast, you just pause it and make sure that you can get this yourself. Let's double check that. That was u to the minus 2 du, which is, raise it by 1, minus u to the minus 1, minus 1 over u, minus 1 over x plus 2, but we're multiplying by minus 7, so that's correct. And this will be the last example. We have degree 2 over degree 3, so it is proper, and it is completely factored. We have one linear factor, x, and we have an irreducible quadratic, x squared plus 2x plus 2. So I would set up my partial fractions to be the integral of, and this rational function would be a over x, x is linear so it gets to constant numerator, plus, now I have to put bx plus c because our denominator is degree 2, or it's a irreducible quadratic. So put it on pause, set up your partial fractions, and solve for a, b, and c. Okay, so this is pretty tricky to solve for a, b, and c. So let me give you a little hint. When you set up these partial fractions, start by letting x, let me write this down in, oh, how about blue? This is just hint. You should be able to solve for this just using your high school algebra. Let x be 0 and get a equals minus 3/2. That was pretty easy. But now there's not an obvious value of x to get the rest. So let x be 1 and let x be minus 1. And you're going to get an equation in b, two equations in both b and c. And you will get b is equal to 5/2 and c is equal to 3. So let's rewrite the integral as the integral of a over x. So that would be minus 3/2. I'm going to pull the a out, times 1 over x dx. Well, that's easy. That's a log. And then we have plus the integral, and b is 5/2, so I'm going to write 5/2 x plus 3 over x squared plus 2x plus 2. So obviously this is the one that's going to give us a little trouble. This integral is minus 3/2 times the natural log of the absolute value of x. So let's circle that in green. We don't want to forget it, but it's going to take us a while to figure out this one. So x squared plus 2x plus 2 is an irreducible quadratic, and I think maybe I'll stay in green here. We want to complete the square. So that's going to be x plus 1, the quantity squared, plus 1. So if we write u equals x plus 1, then du is dx, and we want to change everything into u, because I want this to be u squared plus 1 in the bottom. So it's just too complicated to do it by just seeing a pattern here. We want to solve for x in terms of u. X is equal to u minus 1, and so the numerator here is 5/2 times u minus 1 plus 3. That's the numerator. It's kind of like scratch paper here. So I'm going to expand that, 5/2 u, and then I have minus 5/2 plus 6/2 is plus 1/2. So rewriting this integral, I'm going to write it as the integral of 5/2 u plus 1/2 over u squared plus 1. So I can see I'm going to get a natural log and an arctangent. I'm going to split this. I'm definitely going to factor out these coefficients on the top, so I'm going to write it as 5/2 times the integral of u over u squared plus 1 du plus 1/2 times the integral of 1 over u squared plus 1 du. Well, that's good. That's 1/2 arctangent u. Now up on the other one, once we see it this way, it's not bad. We see if we let u, well, I guess I can't call it u, let's call it w, equals u squared plus 1, then dw is 2u du. So I just need a factor of 2 and another factor of 1/2 out here. So here we have dw over w. It's a natural log. So integrating, I have 5/4 times the natural log of u squared plus 1. Now I have to put it all back in terms of x, but this is 1/2 arctan u. So we can write our final answer substituting back in u equals x plus 1. So the answer is, going up here, we can't forget about that, minus 3/2 natural log absolute x, and then we have plus 5/4 times the natural log of the absolute value, and u squared plus 1 was our x squared plus 2x plus 2, and then plus 1/2 the arctangent of u, which was x plus 1 plus a constant. So we've seen that your linear factors of the denominator give rise to partial fractions that will integrate to natural log. If you have a factor that is an irreducible quadratic, then you should complete the square, make a u substitution, and split the integral in terms of u. Split it out and you'll probably get a natural log and an arc